Okay, so hi everyone to our weekly seminar at the Institute of Astrophysics in Crete. Today we have the pleasure to have with us Stefano Giarratana. So let me introduce him a bit. Stefano is currently a postdoctoral researcher at the Observatory of Brera in Merate in Italy. He graduated at the University of Padova in 2020, and then he moved to Bologna to the Istituto di Radioastronomia for his PhD, during which he worked on radio observations of GRB and other transients, with a particular focus on VLBI observations. He obtained a PhD degree in early 2024, and then he moved to the current institute, where he continues working on radio observations and theoretical also interpretation of GRB afterglow. So thanks for being with us. The floor is yours.
Thank you for the nice introduction. Actually, this is the first time that I'm being invited. So this is the first time they introduced me. So thank you very much for it. And also thank for having me here to explain the radio observations of gamma ray bursts, of course. Before starting, I would also like to thank my collaborators, of course, because they here some of them are listed, but there are many, many more, and they helped me a lot during this year, in which I'm mostly learning, I would say, rather than working. So the outline of the talk will be the following. I will first introduce gamma ray bursts and why they are worth studying in radio. Then I will provide you with some examples of studies of GRBs in which radio observation really were crucial and provided important information. Then I will do the same for very long baseline interferometry studies, and I will also explain what very long baseline interferometry, or VLBI, is, for those of you that are not very familiar with this technique. I will then move on the future outlooks and prospects, and I will leave you with my take-home message. So let's start. Gamma ray bursts are the most powerful explosions observed in the universe. They are observed as brief flashes of gamma and X-rays that can last from a fraction of seconds up to hundreds or even thousands of seconds. When they occur, they can outshine the entire gamma ray sky, as you can see on the right panel with real data by Bazzi. And in these small, short interval of time, an incredible amount of energy is released. We are talking about of an isotropic equivalent energy of the order of 10 to the 48 to 10 to the 54 ergs, which is released in this time fraction. According to the duration of these flashes, we divided gamma ray bursts into long and short, where long GRBs are longer than 2 seconds, and they are usually associated with the collapse of a single massive star, such as Wolf-Rayet star, as depicted in the artistic impression on the upper left panel, while short GRBs are due to the merger of two neutron stars or a neutron star and black hole, as proved by the gravitational wave event 1708-17A. Regardless of the different progenitor, whether it is a massive star collapsing or a merger event, a highly magnetized neutron star or a black hole will eventually be produced. This central engine will accrete material and launch two relativistic jets in opposite directions. In the standard model, multiple shells are ejected, as you can see in this movie here, and when a faster shell catches up with a slower one, here in the movie, inner shocks arise, the electrons are accelerating, they produce gamma and X-ray through synchrotron emission. And this is what I was calling before the prompt emissions, that the brief flashes we were observing. The outflow continues to expand. It sweeps up material from the surrounding medium and interacts with it through external shocks, producing a forward shock that is propagating throughout the medium, the environment, and a reverse shock that is propagating backwards into the ejecta. These two shocks produce an emission that is called afterglow emission, and that can be observed from the very high energy down to the radio band. And this is the phase in which I'm mostly interested in. Before giving you some example of GRB studies in radio, I need to do another small, very short introduction on why it is worth studying GRBs in radio. And I've gathered here 3 main reasons. The first one is that the emission we are observing, that is synchrotron usually, it's slowly evolving in radio with respect, it's slower with respect to the X-rays and optical, and therefore it's easier, in principle at least, to discern between different emitting components, such as the river shock and forward shock I was mentioning before. Also, it is very important because GRBs are one of the few sources in the sky that show a perfect synchrotron emission with the break frequencies, and we can also see in GRBs the evolution of this synchrotron emission in time, in reasonable times, I would say. And in radio, many break frequencies are passing by, so we can actually pinpoint them and actually constrain very well the emission and emitting mechanisms. Another thing we can do is to use the very long baseline interferometry. I will tell you later what that is. To achieve a resolution of the order of milliarc second. And with this incredible high resolution, we can actually study the geometry of the blast wave, such as the viewing angle of the jet or the jet opening angle. But we can also constrain the size and the structure of the emission. For example, if it is a choked jet or a successful jet. So this is very, very powerful, and it provides us with information that cannot be obtained with any other methods or bands so far. Finally, the third one is that the emission in radio is heavily dependent on the surrounding medium profile. Therefore, by studying the emission in radio, we can have some, we can put some constraints on the environment in which the progenitor launched the GRB, and therefore we can have some hints on the progenitor. Indeed, we expect that for a long GRB that is produced by a collapsing star, the star produces a strong wind before exploding and producing the GRB, and therefore the GRB is expected to expand in an environment that has a wind-like profile. While for major events, for short GRBs, we expect the environment to be homogeneous, such as the interstellar medium, or ISM as we call it. Therefore, as I was saying before, by studying the radio emission, we can have some indirect hints on the progenitor's nature that go beyond the simple classification of short and long based on the duration, as I was mentioning before. So the first comprehensive, and I think the only one so far, study on radio observations of gamma ray bursts was done by Chandra and Freire in 2012. These are observations of the afterglow phases I was mentioning before. In this plot, you can see the spectral luminosity as a function of time, so that how the emission, the luminosity of the GRB is changing in time. These are all the detection they got up to 2012. And the red line is, I think, the median of all the detections. There are not the upper limits in this plot here. And the main thing here is that I want to actually say is that while for X-rays, the detection rate of a GRB is 95%, so that more than 9 out of 10 GRBs are detected also in the X-rays. In the optical is 7 out of 10. In radio, we have a detection rate which is quite poor. It's only 30%, so that less than 1/3 are detected in radio. There's an asterisk here because actually more recent studies says that this rate is around 50% now, but this is still a lot less with respect to the X-rays, for example, and this is for sure, at least, due to the fact that the radio facilities are less sensitive with respect to the optical and even more with respect to the X-rays. So I'm now going to give you some examples of GRBs that for which the radio observation were really crucial. And I will start with 2010-15A. This was a burst that occurred on the 15th October 2020. This actually was my first GRB. And this was a low luminosity burst with a hint of very high energy emission, so that above 100 GeV. And there was a detection at around 3 sigma confidence of photons by the MAGIC telescope. And if confirmed, this would have been the 6th GRB detected at very high energies. So for this GRB, we collected X-ray, optical, and radio data. Here, I'm showing you something that will be shown a lot during this presentation, so that what we call the light curves of a GRB, so that flux density is a function of time. In this plot, we can actually see how the emission is changing in time. That's why it's so important. And here in dark blue, the dark blue dots and square are the X-ray data points by Swift XRT and Chandra. Then we have the optical in above in red, green, and purple. And you can see, I cannot see my cursor, but you can see the supernova bump at around 10 to the 1 days. I cannot even see the x-axis, never mind. We can see the supernova bump because we saw that this GRB is a long GRB, so that is due to the massive star, and indeed we saw also the supernova. And we have also the radio at 5 and 1.5 gigahertz in blue and orange, I would say, respectively. So the curves you are seeing here are the modeling light curves. So we have a model, which is a standard one, that we apply to the observed emission in order to infer some properties on the GRBs. In particular, we want to constrain the microphysical and global parameters of the emission. And the main point, a thing that is very famous in GRB physics, is that the model is heavily degenerate. So unfortunately, different sets of parameters can give the same result. And indeed, we cannot say anything if we have only one set of parameters that can describe the emission, if many other set of parameters can do the same. In particular, for this GRB, if we do not include the radio data and we take only the optical and the X-ray, which is what usually the community is doing, the model can explain the data assuming both a homogeneous running medium or a wind-lag profile. And this is a problem because we cannot really discern between the two of them. But if we include the radio, the wind-lag profile is completely ruled out. So in this case, the radio was really fundamental to break this degeneracy and pinpoint the circumburst medium profile. And therefore, my first take-home message is that we can actually constrain the surrounding medium profile and break the degeneracy. The second burst is 2210 This was the brightest of all time, also called the boat. And it occurred on the 9th October 2022, so that 2 years ago, more than 2 years ago. I was doing the math. And to give you an idea on how powerful this burst was, I'm showing you on the lower left panel the count rates for previously well-known bursts. And as you can see, 2210 is orders of magnitude brighter than the previously brightest GRBs, because 1304 27A, I think it was the second brightest before 2210 and you can see the difference in count rates. Since this burst was very, very important, it was an extensive campaign at all wavelengths, from the radio to the very high energies. But in this talk, as you can imagine, I'm going to focus mainly on the radio emission. And I have to explain why, but there is a reason. And the reason is that while the optical and X-rays data can be modeled with many different sets of parameters, let's say, the radio, nobody has explained the radio yet. So the emission we are observing in radio cannot be explained with the standard model we are using. On the right panel, you can see, again, flux density is a function of time, so that the light curves at different frequencies. We have from 15 gigahertz down to 0.15 gigahertz. And there are three main things here that are very important. The first one is that we see, for example, at 5 gigahertz, a variability that is not predicted by the models, and it's not related to scintillation, because there's a discussion on it in the paper, but it's excluded. Then the second thing is that you cannot see it here because I have not included, but there is in the paper actually, the spectrum, so that if we take at a given time all the points at each frequency, but for a given time, the spectrum is completely flat. And this is a problem because we don't expect it from the standard model again. And the third thing is that at 15 gigahertz, so that the upper panel on the left of the right panel, there is a peak, there is a beautiful peak that is zoomed in on the left panel of this slide. And this peak was extremely well sampled. It's the best data set ever we had for GRB. And the peak is at 50 millijansky. To give you an idea on how powerful this burst was, I'm usually dealing with GRBs afterglows, but they are at 50, 100 microjansky, that 2-3 orders of magnitude less bright. And the interesting thing is that with this beautiful peak, we could actually, so we ascribe this beautiful peak to a river shock that is actually self-absorbed. And this, I think, is the second time ever that we can see the river shock in these interesting regimes, so that's self-absorbed. And this was actually done only in radio and in this particular band. So the take-home message for this burst is that, of course, we can complicate things because more radio, more problems. I'm usually saying, so that it's harder if you include the radio to explain everything. But there's of course a pro, that is we can discern between different components. Since in this case we could actually pinpoint the river shock that cannot be pinpointed in any other bands, for this burst at least. The last two GRBs I'm going to present are 241025A and 241026A, so that's the day after. And these were two bursts that were detected by Swift, Fermi, Einstein probe, and SWORM. So for the first one, 241025A, it was detected at the redshift of 4.2, so very, very far away. Here I'm going to show again the flux density function of time, as usual. In black, the black dots are the prompt emission, so that the brief flashes I was mentioning before by Swift BAT. Then there is the onset of the afterglow, so that the second part of the emission, which is well detected by Swift XRT in blue here. And then there are also some proprietary data by Einstein probe as black square that are perfectly consistent with the Swift XRT data. Then we also have the optical R band in red, the near infrared in brown, and then we have three frequencies at 6, 10, and 15 gigahertz of the radio in green, yellow, and orange respectively. There are two things very interesting about this burst. The first one is that we can see a jet break. Actually, I should have pinpointed it here, but around 10 to the 5 seconds, more or less, in the X-ray curve, so that in the blue curves, you can see that the slope is changing and it's becoming steeper. And this is very, very important for GRBs, because with this, we can have an estimate of the jet opening angle. And the second thing is that, for me, it's mostly interesting, actually, is the radio evolution, because we can see actually color evolution in radio. So that if you take the first epoch before 10 to the 5 seconds in the zoom in, you can see that the 6 gigahertz in green is below 10 gigahertz in yellow and below 15 gigahertz in orange. But in the last epoch, around, was it 2, 3, 4, 5, 6, 10 to the 6 seconds, we can see that they have switched. And this is because we think this is due to the fact that the emission is transitioning from an optically thick to an optically thin regime. But this, in the ISM case, which is the one that can explain the rest of the data, is possible only if we assume that there is a lateral spreading, so that let's assume that the jet is a perfect cone. After the jet break, the cone is expanding laterally. And this is something that is usually observed in the optical and X-rays, but it's very, very rare to be observed in the radio. And actually, it's very important because we now can pinpoint also the a jet break without seeing it, but due to the indirect, let's say, effect of lateral spreading. The second GRB is 241026A. This was closer. Again, I'm showing you the flux density function of time, same color as before. We have the prompt emission by BAT in black dots. Then we have the emission by Swift XRT that shows this beautiful plateau between 10 to the 2 and 10 to the, let's say, 4 seconds. And then again, a decaying slope. We have the optical in red, the near infrared in brown, and finally we have the radio data again at 6, 10, and 15 gigahertz, same colors as before. This time we don't see a jet break, but in radio we see again these beautiful color evolutions. So in this case, we can actually, we're still working on it, but we could say probably that there is actually a jet break that is not observed in the X-ray. It's not the first time. It's quite usual, actually, but we cannot say it. So we can say that there is only by seeing the lateral expansion for in the radio curves, because we cannot see a jet break in the optical nor in the X-rays. And usually we see it in the optical at least. But we don't have enough data here. But also, it's this is not the only important thing, but another thing that we cannot really explain right now is the fact that there is a sudden increase at 6 gigahertz. So if we take a look in the zoom in at the 6 gigahertz data, so that the green points, you see the first 2 points before 10 to the 6 seconds. And then there is another point that is actually, you cannot probably see it here, but it's beyond the orange point, the third orange point, and there is a sudden increase of an order of magnitude of emission that has been observed in a few days, which is not explained right now, and we are still working on it. So the take-home messages for these two bars is that we can probably, it's not said yet, we can probably reveal the lateral spreading by looking at the radial light curves only, and this is very, very interesting. I will move on now with the very long baseline interferometry studies of GRBs. So the results we have seen so far are obtained with compact arrays, so that we have antennas that are located on the same site, they are connected through cables, and they're observing the same thing at the same time. In an interferometry experiment, whatever it is, the resolution is directly proportional to the distance between two antennas. So if we take different antennas and we put them very far apart, we can have a better resolution. And very long baseline interferometry means that we put antennas all over the world in order to have a sort of single big dish as large as the Earth. And with this technique, we can actually achieve a resolution of the order of millisecond or even more. For example, EHT that works at higher frequencies reached a resolution of the order of microsecond, tenths of microsecond. And EHT was the collaboration that showed the image of the black hole shadow. So the main arrays that work with very long baseline interferometry at the centimeter wavelengths, let's say 6, 10 gigahertz, what I've showed before, which are the most important bands, I would say, in radio for GRBs, are the European VLV network that has antennas in Europe, South Africa, and China. Then there is the very long baseline array that has antennas, 10 antennas in the US. And finally, there is the long baseline array in Australia and New Zealand. There are many other arrays, as I was saying, also EHT, but they are working at high frequencies, or for example, the East Asia VLV network, or the KVN, and so on and so forth. These are the main three I'm using. So to give you an idea on how powerful this technique is, since one image is worth 1,000 words, I'm going to show you some real data by the XCAT collaboration of an X-ray binary, this time not a GRB. These are radio data, the map you can see, and all the dots you are seeing are all sources observed with this compact array that is MeerKAT in South Africa. The light blue circle you can see is the typical resolution we have with gamma ray satellites, such as Fermi, and is 1 degree, and you can already see that there are like hundreds or even thousands of sources inside, so we cannot discern between them if only one of them is producing gamma ray emission. The yellow contour is the Swift XRT resolution, which is 10 arcsecond, more or less, which is comparable with the MeerKAT one, which is here in white. And both Swift XRT and MeerKAT see this point-like source. But what if we go higher resolution? If we go 3 or even 4 orders of magnitude higher resolution, we can see that this point-like source is not a point-like source. It's a core with a jet and a solder knot. And actually, I think that this is the X-ray binary with the most extended jet ever observed. So this is what we miss if we don't go higher resolution. For GRBs, there are two main scenarios in which VLBI and high resolution is very, very important. The first one is if the GRB is in on axis, so that the jet is pointing directly towards us. That being the case, we can see that the acceleration of the blast wave has an increase of the angular size of the emitting region, as depicted in this movie here. So imagine that we have a central engine, a black hole, that is launching a jet, producing a blast wave, and the blast wave is pointing towards us, the observers. So the two panels perpendicular to the line of sight are two representative observations. And as you can see, as the blast wave is passing from the first to the second observation, on the lower right, you can see that the size in the image is increasing. This was actually done for the first time by Taylor and collaborators for 030329A, so that a burst that occurred on the 29th of March of 2003, so that 22 years ago, a lot. And here you can see the image diameters that what they can actually measure in the map as a function of time. And you can see that there is a clear increasing trend. And this was actually the first direct proof ever of apparent superluminal expansion in GRBs. There were some indirect evidences, such as the compactness problem, but this was the first direct proof, and it was provided by VLBI only. The second time in which we did this was for the boat 221009A, the brightest ever, of course. This plot I'm showing you here is exactly the same as before, with three main differences. The first one is that this is another GRB, because it's not 030329A. The second one is that we include three frequencies and not only one, as done before. And each frequency is a different color. We have in blue 5 gigahertz, in purple 8 gigahertz, and in yellow 15 gigahertz. And the third thing is that we use the Bayesian approach. So this is a violin plot, so that the width of the colored area is proportional to the posterior distribution of the Bayesian fit we performed on the data using a Gaussian profile. So we have the data, we fit them with a single Gaussian. The full width at alpha maximum of this Gaussian is, it's not exactly the size of the GRB, but it's almost the size of the GRB. There's a constant factor. And since we are using a Bayesian approach, the fit is not giving us a perfect number with an error, but it's giving us a posterior distribution for the full width at alpha maximum. And if we take this posterior distribution, in the violin plot, this is proportional to the width of the colored area. So we did this for each observation at each time, at each frequency. The point here is that the narrower the distribution, the better the observation, so that we have a better constraint. And indeed, you can see that in two cases, the first in blue and the last one in yellow, the distribution is really poor, and therefore we have an upper limit, and therefore there are only triangles and not the dots with the error. So once we have done this for each epoch at each frequency, we also perform a Bayesian fit with a single power law on the entire data set to see how the size was changing in time, to see if it was expanding or not. And in the inset, you can see the posterior distribution for the slope. And we have more than 4 sigma evidence that the slope is larger than 0, so that the GRB is actually expanding in time. So this was the second time that we could do this after 20 years from the first time. And the slope that we derived, the median value is 0.7. This is very important because it's cool to see the expansion of something, to be honest, but we should also use this information to, let's say, constrain the dynamics of the GRB. And therefore, we can compare this value with the prediction from models, for example. So a bit of a disclaimer, the prediction depends heavily on the hypothesis you are making on the model. And in this case, we split again the situation in two cases. One is the ISM profile, the homogeneous surrounding medium, and the other one is the wind-like profile. And we are starting from a situation of a jet break, as we have seen before, because there were some claims in the literature of a jet break at very high energies and in the optical way before our first observation. So our slope should be consistent with the post-jet break evolution in principle. So if we start with the ISM, the post-jet break evolution expected for a single blast wave by Blandford and McKee is 1/4, which is more than 3 sigma in disagreement with our findings. So this is not possible, at least from what we have seen. We could have lateral spreading, as I was saying for the other GRBs, and the slope is now consistent. But numerical simulation taught us that the lateral spreading is efficient only for very narrow jets. And therefore, this is not rejected, but it's kind of disfavored, because we should have a very, very narrow jet to have a lateral spreading, in this case at least. We could also have no jet break at all, and the slope again would be consistent. But we have a big problem with the energetic, because if we consider that there is no jet break, the energetic will be above 10 to the 55, I think, ergs, which is too much, which is not reasonable from theoretical assumptions, let's say. We could solve everything if we assume that there is a structure jet, so that the jet that is propagating in the medium is not a perfect cone, but it has an angular structure within the jet opening angle, such as a Gaussian or something. And this is even more realistic, because we don't expect the jet to be a perfect cone launch in the medium, but there are turbulences and stuff before that shape the structure of the jet. And so if we assume the structure jet, the post-jet break scenario is fine. On the other hand, if we assume that the profile is a wind-like profile, the slope is already consistent with what we observe. So this is not very constraining, as you may have understood, but it's beautiful that we can actually do this kind of discussion with the slope only, without light coverage spectra so far. It's very, very interesting. Also, we noted that there were some hints for different size evolution at different frequencies. So we split the data into two groups. One group on the left, 5 and 8 gigahertz only, and the other group, 15 gigahertz on the right. We perform again the Bayesian fit on the slope, so that we took the data and we see how the evolution of the size was at 5 and 8 gigahertz on the one end, and on 15 gigahertz on the other hand. And as you can see in the insets, the slope is consistent, but if we take the contour plot, so that slope and the normalization, because we have two parameters in the fit, the slope and the normalization, we can see that while the slope is consistent, the size, the normalization is consistent within 1 sigma, but not at the, well, it's consistent within 3 sigma, but not at 1 sigma. So we cannot claim anything. That's the take-home message. We cannot claim anything, but there is a hint of different size evolution. And since it's always very funny to take a hint and speculate a bit, so we did it. And we try to assume that at different frequencies, we are observing different emission mechanisms. So that at 15 gigahertz, we assume that the emission is dominated by force shock, the one that is propagating in the surrounding medium, while at 5 and 8 gigahertz, the emission is dominated by reverse shock, so that the one that is actually going backwards into the ejecta. If we assume this, and we can fit the data in the ISM and wind case, respectively on the left and on the right panel, assuming a model that is by my supervisor, Salafia. Here in these plots, you can see that the forward shock is in gray line, while the reverse shock is in red line. If we fit the data, only the size evolution, we can have an estimate on the energetic, which is very, very high in both cases, and therefore to let's say, alleviate this problem, we should assume that the density of the surrounding medium is very, very low. And of course, we also found that the jet is very broad. I'm not going into all the details of this because it's not my expertise, and also because it's speculation. So, so it's funny, but we don't need to go into the details of this. And an interesting thing, though, is that this is with the slope only, as I was saying, but from light curve and spectral analysis by other groups, it was suggested actually that there was a reverse shock dominating at these frequencies at these times, and the forward shock dominating at that frequency at that time. So it's very, very interesting that with complementary observation, we can actually say the same. Actually, for us, it's only a hint, but it's still very, very interesting. Also, since this burst was so bright and so nearby, we tried to observe it with a global VLBI observation, so that we include almost every antenna in the world that can observe at 5 gigahertz. There are more than 55 antennas. I was counting them last day. And here I'm showing you the positive distribution on the slope, on the size in red. And as you can see, first of all, the positive distribution is way narrower. This is because with many more antennas, the signal-to-noise ratio in the map is way higher. This data set is beautiful. And the second thing is that they are 5 gigahertz, so that exactly the same frequency of the blue ones. and they are consistent with the evolution observed at 5 gigahertz by the European VLBI network. And this is very important. And the third thing is that if we take all the data, including also the global one, and perform again a fit with a single power law to see the expansion, we can see in the inset the posterior distribution from the slope is worse. We have more than 5 sigma now, evidence that the GRB is expanding, which is cool because I want a 5 sigma always. But the posterior distribution is worse. Why is that? This is because if we take the first global observation in red and the second to last VLBI observation in yellow, you can see that they are way in disagreement now with respect to before, where they were compared with the blue one, the last blue one. And this is actually a good thing because this is a further hint that we're observing different things at different frequencies. And so when we try to use a single slope to fit 2 different evolutions, we get something that is worse. So this is a further hint. We cannot claim anything again because the VLBI data are not good enough, but the hint is getting stronger and stronger. And this is very, very important. So the other case in which we can actually get some constraints using VLBI in the scenario of GRBs is when the GRB is seen slightly off axis. That being the case, we can see the displacement of the center of the emission as an apparent proper motion as depicted in this movie here. This was very important, and it was done only once for 1708-17A, the famous gravitational wave event. Before going to the VLBI part, I'm going to show you again the flux density as a function of time for this burst. We have the radio in the upper part in gray, and in brown and in red, and then we have the optical in green, and then the X-rays in blue. As you can see, there are 2 models, 2 lines, the dashed line and the solid line, that can reproduce the data. And this is a big problem because we have, again, a degeneracy. The 2 models in particular are, for the solid line, the structure jet, so that not a perfect cone, but a sort of a cone with an angular structure within the jet opening angle, as I was saying before, but seen slightly off axis, as depicted in the sketch on the left. Or for the dashed line, we can have also a choke jet, so that an isotropic emission, not a jet, but an isotropic emission that has a radial velocity profile. And both both models can reproduce the observation, which is a big problem. But VLBI came in, and the first observation when done by Moulay and collaborators in 2018. You can see here 2 maps that are superimposed, so that declination and right ascension. These are 2 radio maps in contour. It's a contour plot, actually. The first observation is in black at 75 days post-burst, and the second one is in red at 230 days post-burst. And as you can see, the center of the emission, the 2 crosses, are shifted by 2.7 milliseconds. And this was the first proof ever that this burst was a slightly off-axis GRB. And therefore, it was pointing towards a structure jet as seen slightly off-axis and not a choked one. But the final evidence came by Giancarlo Ghiland and collaborators using global VLBI observations, everything in the world. And they had a way higher angular resolution, and by comparing the size they were measuring, actually they constrained the, they couldn't measure the size, but they constrained it, they got an upper limit. With the expectation from models, they could actually rule out the choked jet. And this was extremely important because this was also the first proof ever of a successful jet from binary to star merger. This was posited in the 80s by Eichler, and it was confirmed only 40 years after by VLBI observation. And this is the only proof that has been done so far. So the take-home message in this case is that we can consider dynamics such as the expansion and the deceleration of the GRB, and also the structure, whether it is a structure jet or a choked one. I'm now going to focus on the prospects. So I think we all have heard about the square kilometer array. This will be a super facility in South Africa and Australia. It's actually being built right now. And in South Africa, we will have 197 dishes working 40 meter each, working between 350 megahertz and 15 gigahertz. While in Australia, we will have more than 130,000 antennas of 2 meters each. I've seen them, not in Australia, though. Working between 50 and 350 megahertz. So this is going to be a super powerful facility, and therefore it will, of course, impact the GRB science. I have to give you a disclaimer first. The results you're going to see are not updated, because the only study on this, on the SKA impact on GRBs, was done by Giancarlo Ghirlanda in 2013. And at those time, the SKA was a bit over-optimistic, let's say. And now the project has been downsized many times, I would say. So these numbers are a bit optimistic, but it's the only ones that we have. And actually, this year, there was a call to propose papers for the white book, the new white book for SKA. And we're currently working on updating these, the community is working on updating these numbers. So let's take these as what we have so far. So we should pass from around 30%, as I was mentioning before, 30–50%, to almost 100% of detection rate at the peak time. So that whatever we observe, if it is at the peak time, we detect it, which is incredible if you think about it. And on the left, you can see a plot by Giancarlo in 2013. This is the peak flux density as a function of time of the peak, so that when the afterglow emission in radio is passing through our band at 8 gigahertz and is peaking, we take that flux and the time of the peak and we plot it here. The red dots are real detections. The blue triangles are real upper limits that were at those times. And as you can see with SKA2, the sensitivity of SKA2, we should see everything. The gray dots, sorry, are a population of synthesized GRBs produced by Giancarlo. And as you can see, with SKA, we should be able to see everything. Only one dot is outside the line. Also, we should pass from less than 15 to almost 50% of detection at the transition time, so that when the blast wave becomes non-relativistic, so that we have a blast wave that is relativistic and then it's becoming non-relativistic. And the evolution from that point on is described by a set of equations that is independent from the equations that are describing the relativistic case. So we can have a sort of independent way to estimate, for example, the energetic of the burst. So it's very important. But for me, at least, the most important thing is that we can combine the supersensitivity of SKA with the longer basin of the LBI to see the structure and the geometry of the jet of each GRB that has enough signal-to-noise ratio. And we're actually working on this to see how many we can detect in the SKA era. And this is actually very, very appealing, I would say. And of course, we can detect new things because every year there's something new in GRB physics, so we can't know what we are going to observe. And above all, in radio, where we cannot really explain anything, apparently. So to conclude, the radio emission is really, really important because we can actually discern between different components, as we did for 2210A, where we saw this beautiful peak and, due to the river shock. We can see the expansion of the jet, and we can actually, with the constraints on the size, we can tell whether it is a choke jet or a structured jet or whatever. But let's hope that with SKA we could do that for more than 3 GRBs in 25 years. And so my take-home message is that these are all information that cannot be obtained with any other methods of surveillance, and they are really complementary to the study of light curves and spectra. So they provide information that can be very useful to alleviate or even break the degeneracy I was mentioning in the afterglow modeling. And so the take-home message is that the radio is fundamental to study GRBs and, of course, many other sources. Thank you.
Thank you very much. Thanks. I think you fulfill my request of being clear and thorough. So it's I understand. I think I understand. So thank you very much. It was an interesting talk. Let's see if there is any question from online. You can raise your hand, or you can just unmute yourself if you want to speak. Well, I can. Okay, I see one. Yeah, Felix.
Yes, hi Stefano. Really great talk. I had one question. When you showed the light curves of this very bright GRB, it was 221009, I believe.
Yes, this one.
Yes, exactly. So if my eyes were not deceiving me, that it also looks like that you observe this peak at lower frequencies later, right? So is this also the same phenomenon that you showed later, doing with another GRB that could be related to like this lateral spreading that you mentioned?
So actually, this is another thing. We interpreted this as a reverse shock, while in the other case, it's a single forward shock. And I think that in this case, we see the peak because it's simply the reverse shock that is moving towards lower frequencies. So the emission is moving naturally towards lower frequencies. So we firstly detected at 15 gigahertz in a very detailed way, and then it's passing towards lower frequencies. However, I should also say that, as I was mentioning, the emission of this GRB is not at all standard. So I cannot guarantee what we are observing.
Okay, yeah, so the models are still like somewhat degenerate to explain.
Yeah,
this.
yeah, exactly.
No,
yeah.
I see. Okay, thank you.
Thank you.
I may have a follow-up question actually on this, because
Yes.
one of my two questions actually was exactly related to this. So how do you distinguish? You always say here, you always talk here about a reverse shock. How do you distinguish between the reverse and the forward in this case? What makes you tell him?
So that's another good question. So from the, I think from the extrapolation from the X-rays and the optical, what it is observed in radio is too bright and too early on, because this I think is this is a few hours, but it should be 3 hours post burst, which is too early, because to be a peak of the forward shock. And also the emission is not following what we expect from a forward shock evolution. So in principle, we cannot say that this is a reverse shock, well, with the radio only. I mean, actually we can from looking at the temporal evolution, probably we can, but if we have other bands, it's better, because we can see that the extrapolation from the X-rays and optical is not consistent with this being a forward shock. There were other papers claiming that without this peak, claiming that the observed light curves in radio were due to the forward shock, but at this point, it's a bit of a mess, I would say.
Okay. So no certain statement, right? On this is.
Yeah. So yeah, I'm quite confident that this is a reverse shock because it's too early. That's the point.
Okay.
It's too early and too bright for that to be a forward shock emission. Yes.
Okay.
But still.
So you expect some time for the jet to break. Is this the point?
Yes. Yes, that's for sure.
Okay. Okay. If I don't see, well, while people are still thinking, or I don't see, so I may continue with another question, my last question. Can you explain me a bit why you invoke this lateral expansion when you see this kind of transition from an optically thick to optically thin region at certain frequencies? So you have exactly this transition mostly at 6 gigahertz. So wouldn't this just expected if a jet breaks in the to see something similar in its expansion on the same fashion we see, for example, in relativistic jets in active galaxies, that you have some not moving, and you may have also this trend. So lower frequency, when you have some flare, you have lower frequency peaking later on, for example. Wouldn't this also fit in this, just a jet breaking, or I don't just understand why you need this lateral spreading here?
Yeah, sure. So when we have a jet break in the homogeneous, so before a jet break in the homogeneous case, which is the one that can explain this data in the optical and X-rays, we cannot explain them with a wind-like profile, so we have to take the homogeneous scenario. In that case, the self-absorption frequency is not moving before a jet break and after jet break. So in the standard model, so if it is not already in radio, it's not going to pass there, at least until the injection frequency is transitioning below the self-absorption frequency. So the emission should be always optically thick, to say. But if we include lateral spreading, then this break frequency is actually moving towards lower frequencies. So actually we could see this switching only if we introduce the lateral spreading. That's why if we don't introduce it, we don't expect the self-absorption frequency to pass through the bands we are observing. That's why we need it. This is the explanation we gave, but of course it's still a work in progress.
Okay, thanks. Okay, don't see any other raising hands, so then thank you again for your talk and for your time.
Thank you. Thank you.
So bye, everyone. See you next week.
Bye. Thank you.
Thank you again. Bye-bye.